Hello and welcome back to the video lecture series on chapter 6.3 in the Lock 5 textbook. And we finished the last video going over hypothesis test for the cooperation rate of males versus females for the Golden Balls game show. We assumed that the proportions are equal for the null and not equal for the alternative. Made sure that there's a counts of 10 in each category. Or in other words, we had at least 10 successes and 10 failures in both categories. Calculate the pooled sample proportion, which is adding up all of the successes divided by the total sample size. Throw your sample statistics in the formula. So p hat 1, that's the proportion of males that cooperated, minus p hat 2, the cooperation rate of females, and then divided by the standard error, which is this big old messy square root formula, where we're using the pooled proportion for p hat, and then two different sample sizes. And what I did in here, I rounded everything to 3 decimals. So the top is rounded to 3. This denominator, it's really 0.041789, and so on. But if we round to 3 decimals, we get z to be minus 0.33. So if you wanted to get p-value, you can go to normal distribution. I was right there. Normal distribution. For z, make sure you keep the 0 and 1 for your mean standard deviation. We get a negative z-score, negative 0.33. So I'm going to click left tail and make this bottom value the z-score. Make this negative 0.33, click OK, and we get 0.371. But this is not p-value. Two ways to think about this is I need to double that p-value through 2 times 0.371 because the alternative hypothesis is not equal. The other way to think about that is if you click on 2-tail, make this bottom entry minus 0.33. Okay, you have to add both of these areas. The idea is if you're doing a not equal for the alternative hypothesis, you're assuming it's just as likely that women cooperate more than men as men cooperate more than women by that 1.4%, 0.014. Or just remember, double that p-value if alternative hypothesis is a not equal. And we would certainly not reject the null hypothesis. And I kind of thought earlier that the differences are pretty small, 1% differences. So based on this data, we cannot conclude whether males or females are more cooperative. All right, in our next class, we're going to analyze this game a little bit more, break this down into age groups. So in the last one, we didn't compare age groups at all. But notice right here, this is the cooperation rate. So the below 30, females are a lot more cooperative than males. 30 to 40, they're pretty much the same, pretty close. But still, females cooperate more than males. But then the 40 to 50, strangely, the cooperation rate for males increases. And then 50 and above, females, or for males, it's significantly more. So we're going to look at age next time to see if there's a difference between age. It looks like there's something happening with age here. I think it's hard to tell with 100% certainty because these are just dealing with sample data, but kind of interesting. Before we go to our last example on the chapter 6.3 slides, I did want to show you could get at least the p-value using Geogebra. So I'm going to go back here. And I'm going to refer to this data. If you go to Geogebra, click on that probability. Upper left, click on statistics. And click that drop-down menu. We're looking at test for hypothesis test. Click on z-test, difference of proportions. The null, you can't change it. We're assuming that's always going to be 0. Alternative, less than, greater than, not equal. And for successes, we looked at splitting was a success, so 140 out of 269. Group 1 will be the males. And then group 2, I'll make this the females to be 163 out of 305. That's from the female group, 163 split out of 305. Click enter. And notice down here, we've got the standard error, z-score, and then p-value. So this does differ slightly from what I have on the slides. The reason why it differs is here I rounded everything to 3 decimals, and then at the end you just get minus 0.33. But if I allowed more decimals in my calculations, that z-score should be minus 0.3348. And that's why we get a p-value of 0.7378. So if I were to go into the normal distribution and put in a minus 0.3348 and double 0.369, that's how Geogebra gets the p-value of 0.7378. The Geogebra just gives a little bit more decimals. Actually, it's usually a little bit more accurate, unless you keep a lot more decimals in your calculator. All right, I want to look at one more example. All right, pretty common knowledge now that smoking negatively affects a person's ability to become pregnant, along with causing pregnancy during pregnancy, I should say. But we're only going to look at a study collected on data of 678 women who were trying to get pregnant. The two-way table shows the proportion who successfully became pregnant during the first cycle trying and their smoking status. So we've got smokers here, non-smokers, and then those who got pregnant and didn't get pregnant on the first cycle trying. So I want to conduct a hypothesis test with 1% significance to test this claim. And again, for an hypothesis test, in the exam and the final, I'm going to give you these options right here. Or not options, sorry, the steps of a hypothesis test. So I'm going to go through these. Let's state an alternative hypothesis. And I'm going to write these all down. Here, I have put the information right here. So let's write the null hypothesis. We're looking at the two groups. We want to figure out the proportion who get pregnant. So I'm going to say right here, this pregnant group is what we're looking at. This is going to be excuse me. Well, I'm hiding here. These are my successes. Maybe I should put it right here. Successes. So we're going to say P underscore S. Here, let me do N for not smoking. Is equal to P hat S for the smokers. And for the alternative hypothesis, we're going to assume P, those that don't smoke, the N is greater than the proportion that do smoke. So it looks like a kind of common knowledge now, but it looks like does smoking negatively affect a person's ability to become pregnant? So for the null, we're going to assume that that Pn is equal to Ps, but Pn is greater than Pn. And I want to make this a little bit more clear what we're talking about. So I'm going to clearly describe what those parameters mean or represent. So I'm going to say a little sentence here, P hat N is the proportion of women who get pregnant during their first cycle trying that do not smoke. And PS is the proportion of women who get pregnant during their first cycle trying that do smoke. And that's why I put Pn to be greater than Ps. All right, looking down the list. Good got these two, null alternative hypothesis, the parameter described, the observed sample statistic, and standardized test statistic. All right, the observed sample statistic is, in this case, it's p hat underscore n minus p hat underscore s. And in this case, we want to look at the non-smokers, 206 divided by 534. Non-smokers got pregnant the first cycle trying, whereas we had 38 over 135. Total got pregnant. This is my observed sample statistic. So 206 divided by 543 is 0.379. And then 38 divided by 135 to get 0.281. And subtracting those two, I get this to the difference to be about 0.098. This is my observed sample statistic. All right, now we need to get the pooled proportion. That's p hat equals, I'll put total successes over total combined samples. So the total number of successes is the 38 plus 206. And then the total would be the 135 plus 543. So that would equal 206 plus 38 is 244 divided by 678. And that'll get to be about 0.35988, so 360 if we're rounding to 3 decimals. So that's that pooled proportion. And then the standardized test statistic is z equals, and here it's going to be 0.098 minus the null, but the null is 0 in this case because we assume no difference, and then divided by, it's going to be kind of a messy formula, but it's going to be the 0.36 times 1 minus 0.36. And that whole thing's going to be divided by 135. And then plus 0.36 times 1 minus 0.36 divided by the other sample size of 543. 0.098, and it's a messy formula. I'm going to throw it in my calculator to get 0.36. 1 minus 0.36 divided by 135, and then add 0.36, 1 minus 0.36 divided by 543. Then take the square root. I got this to be about 0.04616. Approximate those. Approximately, we'll round this to 3 decimals. Dividing this out, I get 2.123 as my z test statistic. All right, let's look here. We have observed sample statistic, standardized test statistic. Confirm the requirements are met to use a normal distribution. All right, notice right here, there are at least 10 successes and 10 failures in all 4 cells in the two-way table. So we can use normal distribution. So that assumption or requirement, all the proportions need to be 10 or greater to use the normal distribution. All right. Oh, we're almost out of time on this video, so I'm going to conclude right here. In the next video, we'll finish up, calculate the p-value, decision, and write a conclusion. in the next video.